Okay, in this video, we're going to establish some results that we use in computing Laplace transforms. And so we're going to establish these in a rigorous manner. So the first we're going to do, in the previous video, we saw a limit like this one. So we're going to work it out using L'Hopital's rule. In number 2, we're going to prove that the nth order derivative of t to the n is n factorial. And then from there, we are going to show that the Laplace transform of t to the n is actually n factorial over s plus 1. In all cases, n is a positive integer. So for the first one, we've got the limit as t goes to infinity, t to the power n e to the minus st. So again, n is a positive integer. So the first thing we are going to do here is we write this thing in this form. Then we notice that as t goes to infinity, this thing is going to give us the infinity over infinity indeterminate form. So by L'Hopital's rule, when that happens, the limit can be obtained by differentiating the numerator and the denominator separately. So that means not using the quotient rule. So in this case, we're going to have nt to the power n minus 1 in the denominator. We're going to have se to the st. So it's just applying L'Hopital's once. But letting t go to infinity is still giving us the infinity over infinity indeterminate form. So that means we are going to apply L'Hopital's again. Now, if we do this n times from here, then what's going to happen is that the numerator differentiate this n times, then it's going to give us n factorial. And actually, we are going to establish this result in number 2 here. So as you can see, these are related. So if we do this n times, the numerator is going to be n factorial. The denominator is going to be s to the power n e to the power st. Of course, L'Hopital's can be applied repeatedly. Now you're going to see that as t goes to infinity, not 0, the numerator is now a constant, so it's just going to remain n factorial. This is going to go to infinity, so the whole thing is going to go to 0. So that is the result we've already applied or made use of in the previous video when computing Laplace transforms using the integral. So the next thing we're going to want to prove this formula here that we've just used. So the nth order derivative of t to the power n is n factorial. We're going to use mathematical induction to do this. So in mathematical induction, we've got 3 steps. In the first step, we are going to want to check whether this formula is true for some value of n. We can choose any value. We're going to let n be equal to 2. So in that case, the left-hand side is the second order derivative of t squared. So if we differentiate this once, we get 2t. If we differentiate this again, we get 2. So the left-hand side is going to be 2. The right-hand side, of course, we just plug in n is 2. It's going to be 2 factorial which is going to be equal to 2. This is the same as the left-hand side. So we can conclude that the formula is true for n equals to 2. So formula is true for n equals to 2. So that means step 1 is a success. So then we go to step 2. In step 2, we assume that the formula is true for some value of n equal to k. So basically we're just going to assume that the kth order derivative of t to the power k is k factorial. So assume this is true for some value of n equal to k, where of course k is a positive integer as well. Then the last step, which is called the inductive step, we are going to want to prove whether, given that the formula is true for n equals to k, is it going to be true for the next bigger integer? So the next bigger integer is k plus 1. So it's going to be the k plus first derivative of t to the power k plus 1. If the formula is true, then there should be k plus 1 factorial on the left-hand side, because for this one it was just k factorial. So I want to prove whether this is true, given that S2 is true. So to do that, we working on the left hand side. So there are k plus first order derivatives here. So if we split this into the kth order derivative into the first order derivative, and then we're going to evaluate this one. So if we evaluate that one, derivative of t to the power k plus 1 is simply k plus 1 t to the power k. Then the next thing we're going to do is we're going to factor out the k plus 1. So then we're going to get the kth order derivative of t to the power k. But this is exactly the same as what we have in step 2. And in step 2, we have assumed this is equal to k factorial. So going back to this one, so this is going to be k plus 1 times k factorial from step 2. But k factorial times k plus 1 is k plus 1 factorial. And this is now the same as the right hand side. So that tells us that the formula is true. So the formula is going to be true for all values of n. So that is the first one. In the second one, we want to prove that the Laplace transform of t to the power n is n factorial over s to the power n plus 1. So in this one, in step 1, if we let n be equal to 1, then the left-hand side is going to be the Laplace transform of just t which according to the definition is going to be t times integral of t times e to the minus st by tabular integration. So we take the t, we differentiate it, becomes 1. Differentiate 1, we get 0. This one we integrate, so it's going to be over negative s, and then integral of that one is going to be over s squared. Then we match the first one to the second one with a plus sign. So that means the Laplace transform of t is going to be the negative of t over s plus 1 over s squared e to the minus that as the limit t goes to infinity, this times this is going to go to 0. We've just proved that in number 1. So that means that first one is going to be 0. Then when t equals to 0, this vanishes, this becomes 1. So we're going to have, so this is going to be 1 over s squared. Then if we plug in on the right hand side, so remember on the right hand side we've got n factorial over s to the power n plus 1. If we plug in n is 1, that gives us 1 over s squared. This is the same as the left hand side, so that means the formula is true for n equals to 1. Then in step number 2, we assume that the formula is true for n equals to k. So the Laplace transform of t to the power k is going to be k factorial over s to the power k plus 1. So we'll assume that this is true for some value of n equals to k, where k is also a positive integer. Then in step 3, we want to prove whether, given that the formula is true for k, is it going to be true for the next bigger integer. So here we're going to have k plus 1. In the numerator here we're going to have k plus 1 factorial. The denominator is now going to be k plus 2. Remember it was k plus 1 there. So I want to prove whether this is going to be true, given that S2 is true. So again, we're going to work on the left-hand side. So if we start on the left-hand side, the Laplace transform of t to the power k plus 1 is going to be the integral of t to the power k plus 1 e to the minus st dt. If we integrate this by parts once, let u be t to the power k plus 1, then du is going to be k plus 1, t to the power k, let dv be e to the minus st dt. V is then going to be negative 1 over s e to the minus st. So the left hand side is going to be uv. So uv is going to be negative t to the power k plus 1 over se to the minus st from 0 to infinity minus the integral of v du minus 1 over se to the minus st du is k plus 1 t to the power k dt. Now this term, as t goes to infinity, is going to go to 0 by the result we established in number 1. And then this term at t equals to 0 is going to be 0 as well because of this term. This term is 1. This one becomes 0. So this whole term is going to vanish. Then minus and minus there is going to give us a plus. If you factor out the constants, there's going to be k plus 1 in the numerator. Going to be s in the denominator. Then this is going to be t to the power ke to the minus that. But then notice this is just the Laplace transform of t to the power k. So that means we can write this as k plus 1 over s times the Laplace transform of t to the power k. Now from step 2 we have just assumed that that is equal to k factorial over s to the power k plus 1. So this is going to be k plus 1 over s. This is k factorial over s to the power k plus 1. The numerator now becomes k plus 1 factorial. Denominator becomes s to the power k plus 2. This is now the same as the right hand side. So that means at that point we can conclude that the formula is true for all n in the given set. Alright, so thank you very much for watching. This brings us to the end of the video. We hope this is useful. Please do not forget, of course, to subscribe to the channel. And if you've got any questions, you can post them in the comment section. Of course, like the video as well.